In 6.2, we will talk about different forms of energy that can be potentials or kinetic energies. Then we talked about the energy that are relevant to our cellular process, which are free energy and activation energy. Energy is defined as the ability to do work, and it can exist in different forms. That whether it can be electrical, it can be light, it can be a heat energy, it can be chemical energy as well. So the first kind of energy we will talk about is going to be kinetic energy, which is any energy that has to do with in motions. The object has to be in motion to have this energy. So moving objects, they can make changes to happen. They can be able to do work. Energy is the ability to do work. So an airplane currently in a flight, they can crash somewhere and that can cause damage. That is the ability to do work. And they also carry people. That is the ability to do work. And then the slow moving wrecking ball, that wrecking ball can demolish building. They can do a variety of ways. I mean, if you're in the way, that's probably not a good thing, but they have ability to cause changes. And a speeding bullet, they can cause puncture holes in any surface. Walking persons, if you bump into them, you feel that pressures, you feel that change. That is ability to work. That is kinetic energy that you are feeling. And then other example that you don't really think about is the rapid movement of the molecules within the air, like that's basically wind that can produce heat. That would be considered kinetic energy as well because there's movement of air molecules. Or electromagnetic radiations that would also be considered kinetic energy as well because the radiations are moving, the wave are actively moving, and you'll feel that as heat on your skin if you're under the sun. The second form of energy is going to be potential energies. The potential energy is defined the potential to do work or the ability to do work, but it's not currently doing work. It is just the potentials. So when you have a ball that is raised up by either a string or a person or a crane, if we were to release it, it will be able to do work. So that it has that potential, that store energy within within the ball. Lastly, we have the third form of energy. We call them chemical energy. It is technically a subset of potential energy, but here it's standing on its own because it is a potential energy that exists within chemical bonds. So you can see here, this is gasoline, this is octane. Octane has 8, oct stands for 8 carbon, and it all has single bond, so it is an alkane. This is ending with ane, a suffix anes. So this is a Lewis structure. This is a balls and sticks structures that you can see here of octane. And octane, when you burn octane, it will release energy to power your cars. But those energy come from these chemical bonds. So when you break bond, you will release the energy. When you form the bonds, you will have an energy input or absorb energy. So when these bonds are here, it was formed at a certain time. It stores those energy as potential chemical energy. When you break them by burning them, you can release the energy, and those can be used to do work. Then this is an example where you can see energy transfer between kinetic energy and potential energy. So you have this ball right here that currently raised above the ground. This is the ground. This is raised above the ground at a certain point. At this point, when it is being held up like that, the potential energy will be 100%. If it starts falling, let me go back for a little bit. At this point, the potential energy will be 100% and the kinetic energy will be 0% because they're not moving. It has all the potential to move, but it's not moving. Once it starts moving and falling down, the kinetic energy will actually start to increase, and the potential energy will not be there anymore. They will start decreasing from 100% to lower and lower. So somewhere midpoint in the middle, you will have 50% kinetic energy and 50% potential energy because you're just losing more. You're gaining more kinetic energy and losing more potential energy up until the point where right before you're hitting the ground, You will have maximum number of kinetic energy at 100%, and you will have minimal amount of potential energy, which is 0%. And that's how the ball falling works between the energy conversion between kinetics and potential energy. And it's notice here it's right before hitting the ground. It's not hitting the ground because when it hits the ground, everything sort of stops for a moment. Your kinetic energy and potential energy will both be at 0, and that will be more complicated stuff that physics has to deal with. We don't have to worry about that. The important things here that you need to understand is that energy can be converted from potential to kinetic energy, and that can be observed here through the ball. You also see other example in real life where you have potential energy as stored water that is stopped as a dam here, and that stored water can go through and turn a turbine in order to generate electricity. Or you will have this river, water from the ocean evaporated and it rained on top of a mountain, and that will flow down to form a rivers. And that rivers initially on high on the mountain will have a lot of potential energy. As they're going down because of gravity, they're gaining more kinetic energy and will be losing their potential energy until they reach the sea levels. So these are two more examples that you can see in real life. Then we have to talk about free energy because that is the energy that are relevant to our chemical reactions. Free energy, or it has another name, Gibbs free energy, denoting as G, the capital letter G's. I call it Gibbs free energy because of a scientist whose name is Gibbs that is inventing this process. Gibbs free energy is defined as a usable energy or energy that is available to do work, or specifically that availability to do work will be used to perform chemical reactions. We won't be counting entropy into this. So in order to calculate entropy, we can't really tell the free energy of an individual substance or of a reactant or a product. However, we can tell the change of free energy after a reaction that can occur. Thus, you can see this delta symbol right here. That's delta G. That delta G equating the change in free energy. Same with delta H, delta S. So delta S is the change in entropy. Delta H is a change in enthalpy. Entropy is, for now, you can define it as a system randomness or disorder. We'll go through more of it when we talked about the thermodynamics, the laws of thermodynamics. And enthalpies is the system total energies. So in order to know the change in energy, we have to know the system enthalpy and the system entropy, as well as the absolute temperatures. So these temperatures will be in Kelvin, it won't be in Celsius, and this is the equation that you can use to convert from Celsius to Kelvin. So your delta G will be equal delta H minus temperatures times delta S. So you have to take the entropy, the temperatures, and the enthalpy into account in order to calculate delta G. Delta G is oftentimes actually calculated as standard conditions. So we also have standard free energy of reactions, or delta G naught. So we read delta G naught. This symbol is not degree, it's not. It just means that it is at standard conditions. And we define standard conditions as 7 pH. It has 25 degrees Celsius, which is almost like room temperatures, and at 1 atm pressures. And the units for standard free energy is oftentimes in kilojoule per mole, or sometimes you will see it as kilocalorie per moles as well. And this kilocalorie is equivalent to the capitalized C calorie that you see in the package of food. But oftentimes you will see it as kilojoule per mole. Kilojoules is a unit for energy. Then from your delta G, you can tell if a reaction is a spontaneous reaction or not. So we have to first define what is a spontaneous reaction. A spontaneous reaction is any reaction that can occur without an addition of energy input into the system. Spontaneous here does not mean that it is quickly or suddenly. Spontaneous here means that it will occur without additions of energy. So, for example, rusting iron, where iron will react with oxygen to form iron oxide, it is a spontaneous process, meaning it will happen automatically without any input of energy, but it occurs it takes a really long time for that to occur. So that is not an instantaneous process. It's not suddenly, it's not quickly. Another example that you see is the sugar breaks down into to form energy. That is a spontaneous process, but that process do not occur instantaneously. So here, basically, you know that spontaneous reaction do not occur quickly or suddenly. They occur without an addition of more energy input. So from your delta G calculation, from the change of Gibbs free energy, you can tell if a reaction is spontaneous or not. So if your delta G is negative, you will release energy, and that is a spontaneous reaction. We also call that reaction an exergonic reaction. It is defined as any chemical reaction that can release free energy. If your delta G is positive, your chemical reaction will absorb energy in order for it to occur. Thus, that is not a spontaneous reaction. We call those reactions that requires energy input as an endergonic reactions. So in this figures, in this graph, you can actually see the difference between an exergonic and an endergonic reactions. So on your y-axis, you have Gibbs free energy. On your x-axis, you have time. As reactants proceed into product, same thing here, reactant proceed into product. In an exergonic reactions, your delta G is negative. You will take the Gibbs free energy of the product minus the Gibbs free energy of the reactants to get the change in Gibbs free energy. And here the product has lower Gibbs free energy than that of the reactants, so your delta G will be negative. That is going to be your exergonic reaction. So you see this curve going down like this. If the curve going from lower energy reactant to higher energy product, your Gibbs free energy will be a positive numbers, and that will make it an endergonic reaction. So on the test, you have to be able to tell from the graph if it is an exergonic reaction or an endergonic reactions. Just to relate this to the anabolic and catabolic processes that we talked about before, anabolic processes are endergonic process because you need energy to to assemble more complex molecules, and catabolic process are exergonics because you will be releasing energy as a result of cutting up complex molecules. So this is example, when you break down sugar into simpler molecules, you release energy, thus that it is a catabolic reaction, or it is an exergonic reactions. These are more of real-life example that you will see. So a compound style decomposing, there will be more disorder because you're breaking down molecules. You will release heat, so the total system will heat will actually increases. For your exergonics, it is an exergonic reaction because delta S is actually increasing and delta H is increasing. So your entropy and enthalpy is increasing. For a chick developing for a chick to develop from a fertilized eggs, you actually decreasing disorder because you're forming more complex molecules and cause a orderly form creatures like this, and your delta H is actually decreasing because you're using the total energy to put into forming those bonds. Remember, forming bonds, you're absorbing energy, breaking bond, you're releasing energy. So thus that is an endergonic process. So as this center arc destruction, there's more order. When you're destroying it, you're increasing delta S, you're increasing disorder. Thus that makes your delta G becomes basically more negative, so it is an exergonic reaction. It will release energy. And another example is a ball rolling down a hill. Your delta H, you're basically using converting that potential energy to kinetic energy and lose heat in the process. So that will affect your enthalpy, and that will make your delta G affect your delta G as well. And it is an exergonic reactions. Most chemical reactions that you see so far are reversible. You can go one way or going the another way. An example that you can see here is the breaking down of the building up of a protein molecule. So you can break down protein into individual amino acid, or you can use individual amino acids to form a more complex protein structures. There's a concept called chemical equilibrium. It is a state where you have the lowest amount of free energy possible and the maximum amount of entropy or disorder. It is important in metabolism and energy is because because when we're trying to push away from the state of equilibrium, we're actually requiring energy, and that's what's happening inside our living cells. In our living cells, all the chemical reaction will constantly cause our body going to equilibrium, but it will actually never reach it. And we're actually trying to fight away from equilibrium and from disorder is because we're trying to form more complex molecules. We are a more complex organism. We are in structures. So because all of that, we actually require constantly energy input. And that makes us an open system. That means that that allow for nutrient and waste exchange or allow for energy exchange. That's an open system. Within a closed system, you won't be able to do material exchange at all. And if we have this, we basically won't eat or won't excrete waste, and we would die. That would not be a good thing. And all of these energy that is required for powering our cells to keep us alive, that's actually coming from the sun. And plant is very important. Remember in 6.1, we said that the most productive and important biological reaction is photosynthesis, is that in plants, they convert sunlight energy into chemical energy in form of sugar that we can use in order to drive our cellular respirations and survive and grow as the human beings. Lastly, before we will end, we talked about activation energy. It has to do with the energy used to jumpstart the reactions. So you can see here, the reactant needs to go uphill a little bit in order to go downhill and become a product. So this uphill from this point to this point of the purple line, that will be your activation energy. And when you input an enzyme, that will lower the activation energy and cause them to become this green line right here, where you don't have to go up as high of a hill in order to cause the reaction to occur. So that's why enzymes actually speed up your chemical reaction by lowering the activation energy. So exergonic reactions also requires an input of energy to occur as well. That input of energy will destabilize your reactants, cause them to become into a transition state, where we call that's the intermediates right here. So we have an intermediate right here for an uncatalyzed reaction. Your intermediate energy will be right here for a catalyzed reactions. The intermediate is very stable, it's very unstable, and it has the highest energy. That's why I prefer not to be there, and it will go toward the lower states of energy so that it can be more stable. And more stable molecule is actually preferred. The activation source, the activation energy source is actually heat from the surrounding. So as the system occurs, they'll just absorb heat from the surrounding, and up to a certain point when they have enough energy, they will start to react. And more heat will cause more reactions. However, as you see, heat can also alter with the enzyme later on, so we have to be careful. So the activation energy will determine reaction rate, because the higher activation energy, the slower the reaction rate, and the lower the activation energy, the higher the reaction rates. So iron rust, they have really high activation energies, so they require that that time in order to absorb enough energy to make the reaction to occur. Burning fuels is also another example. If you leave the fuels there normally, it wouldn't burst into flame, it wouldn't cause energy to release, so you have to have a spark to have that initial input of energy given by that spark. For our cellular reaction, for most of our reaction, is actually have a really high activation and energy. So if we just leave it alone without enzyme, our body will just die and disappear because we won't be able to perform all the biological processes, and it won't be fast enough for our cells to actually survive. So we have to use enzyme and catalysts to speed up these reactions. Though this is a good thing that enzyme exists, and that most of our cellular reaction has really high activation energy, because if it has a low activation energy, it would be too spontaneous, and the reaction would just occur left and right in our body. Our component would be actually disintegrate, and we won't be a human being anymore. So it is actually a good thing that we need enzyme to overcome this supply heat of energy to allow for reaction to occur. That's conclude our 6.2. We will talk about 6.3 next.